What happens when a star collapses into a point of no return? In 1971, scientists found the first real evidence of such an object, Cygnus X-1, the very first black hole ever detected. Today we'll explore how this cosmic mystery was uncovered. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, what do you find most mind-blowing about black holes? Thank you for watching. Now let's begin. In the northern sky, within the constellation, Cygnus lies a stellar system that appears faint and ordinary to the unaided eye, but that under careful study reveals extraordinary properties. The system consists of a visible blue supergiant star and an unseen compact companion. The visible star is recorded in the Henry Draper catalogue as number 226,196. It is an object of immense size and power, radiating strongly in ultraviolet light and carrying the spectral classification O9.7 ISAB. This classification marks it as a hot and evolved supergiant burning its nuclear fuel rapidly and shedding large amounts of matter into space through a strong stellar wind. Its mass is estimated to fall between 20 and 40 times that of the Sun, and its radius is about 20 times solar. The outer layers of the star are unstable, driven outward by radiation pressure and producing a continuous outflow of gas moving at high velocity. The companion in this system does not emit visible light and cannot be seen directly. Its presence is inferred from the way the blue supergiant moves. When the light of Henry Draper, catalogue number 226,196, is dispersed into a spectrum, absorption lines appear corresponding to elements in its atmosphere. These lines do not remain fixed but instead shift rhythmically. Over a cycle lasting about 5½ days, the lines move toward shorter wavelengths, then toward longer wavelengths, and then return to their original positions. This pattern is caused by the Doppler effect as the star moves toward and away from Earth in a repeating orbit. The regular motion demonstrates that the visible star is bound to an unseen partner, circling a common center of mass. The amplitude of the velocity shifts shows that the compact companion must have considerable mass. Ordinary stars that are bright enough to match this mass would be visible in optical light, but no such star is detected. The gravitational effect required is too large to be produced by a planet or a low-mass star. Instead, the data indicate the presence of a dense and compact object. The orbital period is stable, repeating with precision, and provides a reference for observing changes in the system across all wavelengths. Gas expelled by the blue supergiant in its stellar wind does not escape freely into space. A fraction of it is intercepted by the gravity of the unseen companion. Because the gas carries angular momentum, it cannot fall directly onto the compact object. Instead, it forms a spiraling flow known as an accretion disk. In the disk, turbulence and friction cause the gas to lose angular momentum and move inward. As it does so, gravitational energy is converted into heat. Temperatures rise until the gas emits radiation in the form of X-rays. The innermost regions of the disk are heated to tens of millions of degrees Celsius, far hotter than any surface of an ordinary star. The result is a bright and persistent X-ray source detectable only by instruments above Earth's atmosphere. The system is located at a distance of about 6,000 light-years from Earth. At this distance, the observed X-ray flux corresponds to a total luminosity tens of thousands of times that of the Sun. Such power cannot be explained by nuclear fusion in a normal star. It requires the release of gravitational energy from gas falling deep into the potential well of a compact object. The X-ray emission is not steady but varies on timescales ranging from seconds to less than a second. These rapid changes show that the emission originates in a very small region. The principle of causality dictates that no object can vary faster than the time it takes light to cross its own diameter. Sub-second variability therefore restricts the size of the X-ray source to a region only a few hundred kilometers across, consistent with the expected dimensions of a stellar mass black hole. The optical spectrum of the blue supergiant reveals additional information. Besides orbital shifts, the lines show evidence of the star's stellar wind. Broad profiles and asymmetries indicate that gas is moving outward at high speeds. This wind is structured and clumpy, influenced by the intense ultraviolet light of the star and the X-rays from the compact object. When clumps of gas pass through the line of sight, they partly absorb the X-rays, causing dips in brightness. By analyzing these changes, astronomers gain information about the distribution of gas around the system. The wind not only feeds the black hole, but also interacts with the radiation from the accretion disk, creating a feedback loop that shapes the behavior of both stars. The recognition of this system as an X-ray source began in the early 1970s, when satellites equipped with X-ray detectors surveyed the sky and discovered bright sources that could not be explained by ordinary stars. Among the brightest was the source in Cygnus, which was soon associated with the blue supergiant. The identification was made possible by comparing the X-ray position with optical catalogues. Once the connection was established, astronomers focused attention on the binary measuring its spectrum, orbit, and variability. Within a few years, the evidence pointed toward the interpretation that the unseen companion was a black hole. This was one of the first times that such a conclusion had been drawn with strong observational support. At the distance of 6,000 light-years, the binary appears as a single point of light in small telescopes, but instruments that probe different wavelengths show its complex nature. Optical spectroscopy tracks the orbit of the star. Ultraviolet observations show how its wind interacts with radiation. X-ray telescopes record the heat and variability of the accretion disk. Radio telescopes detect faint emission possibly related to outflows or jets. Together, these observations reveal a system where an ordinary star is gravitationally bound to an extraordinary compact object, each influencing the other through mass transfer radiation and orbital motion. The combination of measurements demonstrates how astrophysicists can study objects that cannot be seen directly. The compact object has no surface and emits no visible light, yet its mass and presence are revealed by the orbit of its companion and by the radiation released as it consumes stellar wind material. Each line in the spectrum, each fluctuation in brightness, and each cycle of orbital motion adds evidence. The binary in Cygnus has become one of the most carefully studied laboratories for understanding compact objects, accretion processes, and strong gravity. The path to the recognition of this binary as the first widely accepted stellar mass black hole is rooted in the development of X-ray astronomy during the 20th century. For centuries, astronomy was confined to the visible spectrum, first through naked eye observation, and later through telescopes. This changed in the middle of the 20th century, when detectors sensitive to X-rays were carried above Earth's atmosphere on rockets. Because the atmosphere blocks X-rays completely, these high-energy photons can only be studied from space. Early experiments revealed that the sky contained sources much brighter in X-rays than had been expected, indicating processes more energetic than ordinary starlight. This realization opened an entirely new field of study. In 1964, one of the first rocket-borne X-ray detectors recorded signals from the Crab Nebula, a supernova remnant. This discovery confirmed that cosmic objects could emit X-rays detectable from space. Over the next decade, improved detectors were launched, culminating in 1970, with the Uhuru satellite the first dedicated X-ray observatory. Uhuru surveyed the entire sky and catalogued hundreds of sources. Among them was a bright and variable emitter located in the constellation Cygnus. It was labelled Cygnus X-1 with the suffix, indicating that it was the first strong X-ray source found in that constellation. Cygnus X-1 distinguished itself through several properties. Its X-ray flux was persistent, unlike many sources that appeared only briefly. It also varied on timescales of seconds, implying a small emission region. The intensity was too high to be explained by normal stellar activity, suggesting that gas was being heated to millions of degrees by accretion onto a compact object. Still, the identification of the optical counterpart was required before firmer conclusions could be drawn. Astronomers matched the X-ray position with the bright star Henry Draper catalogue number 226,196, a blue supergiant visible with modest telescopes. The chance alignment of such a luminous star with an intense X-ray source was unlikely, so the association was considered secure. Once the optical counterpart was identified, attention turned to its spectrum. The absorption lines of hydrogen and helium shifted back and forth, with a period of about 5.5 days. This revealed that the star was orbiting around an unseen companion. Using the amplitude of the velocity shifts and the orbital period, astronomers calculated the mass function, which placed a lower bound on the mass of the hidden object. The result exceeded 3 solar masses, the maximum theoretical mass of a neutron star. This strongly indicated that the unseen companion was a black hole. At first, the conclusion was controversial. Some scientists proposed that the compact object might still be a neutron star if the inclination of the orbit were more face-on than assumed, which would reduce the inferred mass. Others suggested exotic states of matter not yet understood. But as data accumulated, the estimates consistently favoured a mass well above the neutron star limit. The orbital motion combined with the X-ray variability pointed to an extremely compact and heavy object. Within a few years, the consensus formed that Cygnus X-1 contained a black hole. This marked the first time that a specific astrophysical system had been widely accepted as hosting such an object. The discovery came at a time when black holes were still largely theoretical. General relativity had predicted them decades earlier, but many astronomers were skeptical that they could exist in reality. The identification of Cygnus X-1 changed that. Here was a system where the evidence demanded a compact object of more than 10 solar masses invisible in ordinary light, but radiating strongly in X-rays through accretion. It was the first solid case that black holes were not merely mathematical curiosities, but real members of the stellar population of the galaxy. The impact on astronomy was immediate. Cygnus X-1 became a reference point for interpreting other X-ray binaries. The methods developed identifying the optical counterpart, measuring radial velocity shifts, calculating the mass function, and comparing with theoretical limits were applied to other systems. Soon more candidates emerged, but Cygnus X-1 remained the benchmark. Its combination of a luminous optical star, a well-defined orbit, and a persistent X-ray source made it ideal for study. The early observations also set the stage for later refinements. The orbital parameters measured in the 1970s have been confirmed and improved by subsequent decades of observation. The distance has been measured precisely by very long baseline interferometry. The mass of the black hole has been pinned down to between 15 and 20 solar masses. Its spin has been estimated through modelling of the X-ray spectrum. Each step in the process has reinforced the original conclusion. The companion of Henry Draper, catalogue number 226,196, is not a neutron star, not an exotic compact star, but a black hole. The recognition of Cygnus X-1 as the first confirmed black hole system represents a milestone in astrophysics. It showed that black holes are not rare and inaccessible, but can be studied through their effects on nearby matter. It validated X-ray astronomy as a powerful tool and demonstrated the importance of space-based observation. Without satellites, the X-rays from Cygnus X-1 would never have reached detectors on Earth. The system became a symbol of the shift from theory to observation in the study of strong gravity. Even today, the story of Cygnus X-1 serves as an example of how astronomy advances. New technology opens a new window, an unexpected object is discovered, evidence accumulates, alternative explanations are tested, and a consensus forms. The journey from the first detection of an unusual X-ray source to the acceptance of a black hole took less than a decade, but it required a combination of innovation, persistence, and careful interpretation. Cygnus X-1 was not simply discovered as a black hole. It became one through the gradual building of evidence. A binary system such as the one in the constellation Cygnus is best understood by examining how two very different stars can interact so closely that the fate of one shapes the destiny of the other. In this pair, one star is the luminous blue supergiant Henry Draper Catalogue number 226,196, and the other is an unseen compact object whose gravitational influence dominates the dynamics. The interplay between them transforms a stellar wind into a source of high-energy radiation, revealing the mechanisms of accretion that occur when ordinary matter encounters extraordinary gravity. In many binaries, both stars are visible, and their motions can be traced directly. But in this case, only one star shines in optical light. The other reveals itself through the process of accretion. The blue supergiant continually expels gas in a wind driven by radiation pressure. The wind is massive, dense, and fast-moving outward at speeds greater than 1,000 kilometers per second. Left alone, this gas would disperse into interstellar space. Instead, some of it crosses the gravitational boundary of the compact companion. Once captured, the gas accelerates inward. Because it carries angular momentum from the orbital motion of the system, it cannot plunge directly but must spiral. This spiraling motion leads to the formation of an accretion disk, the defining structure of such systems. The disk is not static. Gas orbits rapidly while simultaneously moving inward. Collisions, viscosity, and magnetic turbulence cause angular momentum to flow outward and mass to flow inward. The closer to the compact object, the faster the gas moves and the more energy it releases. Gravitational potential energy is converted into heat, raising the temperature to tens of millions of degrees Celsius. At these temperatures, the gas radiates in X-rays. The result is that a fraction of the blue supergiant's wind, once part of a normal stellar atmosphere, becomes the source of one of the brightest X-ray signals in the sky. This transfer of matter provides not only radiation, but also the key to measuring the hidden mass. The orbit of the blue supergiant is shaped by the gravity of the compact object, and the compact object in turn is sustained by the wind of its partner. Each depends on the other. The optical star feeds material into the disk, while the compact companion transforms that material into X-rays. The disk acts as an engine that channels the gravitational energy of infall into observable light. Systems of this kind are called X-ray binaries, and they are divided into two categories. High-mass X-ray binaries, such as this one, have donors that are massive stars like O-type or B-type supergiants. Low-mass X-ray binaries have small donor stars, often red dwarfs that transfer mass more steadily through Roche lobe overflow. The distinction matters because it shapes the accretion process. In a high-mass system, the stellar wind is irregular and clumpy, producing variability. In a low-mass system, the transfer can be steadier, producing a more stable disk. The variability observed in the system in Cygnus is consistent with the wind-fed model. The accretion disk is only part of the story. Above the disk is a hot region of electrons known as the corona. Soft photons from the disk scatter off these electrons, gaining energy in the process called inverse Compton scattering. This produces hard X-rays, extending the spectrum into higher energies. The corona is dynamic, fluctuating in density and temperature, and it contributes to the rapid variability of the system. Observations show that in certain states the corona dominates the emission, while in others the disk dominates. The transitions between these states reveal how the accretion flow changes, sometimes within days. The binary orbit itself is compact. The two stars circle their common center of mass in about 5.5 days. This means that the distance between them is only a few times the radius of the blue supergiant. The compact object lies close enough to intercept a significant fraction of the stellar wind. At the same time, the proximity distorts the shape of the visible star, pulling it slightly out of spherical symmetry. This distortion leads to small variations in brightness over the orbital cycle called ellipsoidal variations, which can be detected with precise photometry. These variations confirm the gravitational influence of the unseen companion. The small size of the X-ray emitting region is demonstrated by rapid fluctuations. Brightness changes occurring in less than a second imply an emitting region comparable to the distance light can travel in that time, which is less than 300,000 kilometers. This is tiny compared to the size of the blue supergiant, which has a diameter tens of millions of kilometers. The compactness of the source confirms that the radiation originates close to the compact object, consistent with accretion onto a black hole. The accretion process is efficient in terms of energy release. When matter falls onto a black hole up to 10% of its rest, mass energy can be radiated away. By comparison, nuclear fusion in stars converts less than 1% of mass into energy. This difference explains why even a modest flow of gas from the stellar wind can produce an X-ray luminosity tens of thousands of times that of the Sun. The efficiency of gravitational energy release is one of the reasons black holes are such powerful sources. The interaction between the two stars is not one-sided. The X-rays from the compact object ionize parts of the stellar wind, altering its structure. Ionized gas is more transparent and less able to exert radiation pressure, so regions exposed to X-rays may accelerate differently than regions in shadow. This creates asymmetries in the wind, which in turn affect the rate of accretion. The binary is therefore governed by feedback. The wind feeds the black hole, and the black hole's radiation modifies the wind. Observing these effects requires careful comparison of spectra across different orbital phases, because the line of sight passes through different regions of the wind as the stars move. The system provides a clear example of how invisible objects can be studied indirectly. No telescope can image the black hole directly, but its presence is revealed in every spectrum light curve and orbital measurement. The orbit of the visible star, the X-ray luminosity, the variability and the spectral features all point to a massive compact object. Each piece of evidence fits together into a consistent picture. By understanding this system, astronomers also gain insight into the life cycle of massive stars. The compact object must once have been a star even more massive than the blue supergiant. It exhausted its fuel, collapsed, and formed a black hole. The fact that the binary survived that event shows how strongly bound it was. Now the remaining star continues its own evolution, while feeding its companion and marking the presence of a black hole through its own motion. The accretion disk around the compact object in this binary system is the physical engine that transforms captured gas into the X-rays detected on Earth. when the stellar wind from Henry Draper Catalogue number 226,196 is intercepted by the compact object's gravity, the gas does not fall directly inward. Because it carries angular momentum, it begins to spiral. This spiral motion forms a flattened rotating disk around the unseen companion. Within the disk, matter moves on nearly circular orbits while slowly losing angular momentum through turbulence, magnetic instabilities and friction. The loss of angular momentum allows gas to migrate inward, closer to the black hole where the gravitational potential is deeper and the energy released is greater. The physical conditions in the disk change dramatically with distance from the compact object. At large radii, the gas is relatively cool, radiating invisible and ultraviolet light. Moving inward, the temperature rises sharply. The gas glows in soft X-rays, then in hard X-rays as it approaches the innermost stable circular orbit, predicted by general relativity. For a non-spinning black hole, this orbit lies at 3 times the Schwarzschild radius, but if the black hole rotates, the orbit can be closer. For a mass of about 15 to 20 times that of the Sun, the Schwarzschild radius is about 45 to 60 kilometers. Thus, the inner edge of the disk may be only a few hundred kilometers from the event horizon. At that distance, the orbital speed of the gas is a significant fraction of the speed of light, and the photons that escape carry the imprint of relativistic effects. The emission from the disk is not uniform but stratified. Astronomers often describe the disk as a series of concentric zones. The outermost zone emits optical and ultraviolet light. The intermediate zone produces extreme ultraviolet radiation. The innermost zone radiates strongly in X-rays. The corona above the disk adds another layer where photons scatter off hot electrons and gain additional energy. Together, these zones create the broad spectrum observed from the system extending from the optical into the hard X-ray band. Instruments aboard satellites separate these components, fitting models that describe the temperature profile and geometry of the disk. One of the most striking observational features of the disk is the iron K-alpha emission line. When X-rays from the inner disk strike iron atoms, they can eject inner electrons, leading to a fluorescence line at a characteristic energy. In Cygnus X-1, this line is broadened and skewed. The broadening arises from the Doppler effect as atoms move at relativistic speeds in the disk. The skewed shape with a long tail to lower energies is caused by gravitational redshift near the black hole. The detection of such a line provides direct evidence that the accretion disk extends into the relativistic regime where spacetime curvature is strong. Modeling this line has been one of the key methods for estimating the spin of the black hole. The disk is also variable. It does not shine with constant intensity but fluctuates on many timescales. Rapid flickering is caused by turbulence and instabilities in the flow. Slower changes reflect variations in the supply of gas from the stellar wind. Sometimes the system enters a high soft state where the disk dominates the emission and the spectrum is smooth. At other times it enters a low hard state where the corona dominates and the spectrum is harder. These state transitions occur irregularly and are thought to be triggered by changes in the accretion rate or the magnetic structure of the disk. The transitions are accompanied by changes in timing properties, spectral features, and radio emission, suggesting that the geometry of the disk and corona is reorganized. The efficiency of energy release in the disk is remarkable. As matter falls inward, up to 10% of its mass energy is converted into radiation. By contrast, nuclear fusion in stars converts less than 1%. This difference explains why the accretion of only a modest amount of stellar wind can produce an X-ray luminosity tens of thousands of times that of the Sun. The disk around the black hole in this system is therefore one of the most powerful engines in astrophysics. even though the amount of matter involved at any given time is small compared to the mass of the star. The presence of the corona complicates the picture. The corona is a region of hot electrons situated above and below the disk. Its exact geometry is uncertain, but observations suggest it is compact and located near the black hole. Photons from the disk enter the corona scatter multiple times and emerge with higher energies. This process, known as inverse Compton scattering, produces the hard X-ray component of the spectrum. The properties of the corona, such as its size, shape, and temperature, are inferred from timing and spectral studies. Variability is often stronger in the hard X-rays, indicating that the corona is more dynamic than the disk itself. The interplay of disk and corona is revealed by time lags. Sometimes variations in hard X-rays precede variations in soft X-rays, and sometimes the reverse occurs. These lags, measured in fractions of a second, provide information about the distances within the system. They show that the disk and corona are tightly coupled, and that changes in one region quickly influence the other. This coupling explains why state transitions involve simultaneous changes in both components. The disk also interacts with the stellar wind of the supergiant. X-rays from the disk ionize parts of the wind, reducing its opacity and altering the flow of matter. The wind in turn modulates the accretion rate, feeding the disk with varying intensity. This feedback loop makes the system complex and variable. Monitoring across different orbital phases reveals how the line of sight passes through different regions of the wind, affecting the observed spectrum. Absorption features vary, with phase mapping the structure of the wind and its interaction with the X-ray source. Although the accretion disk cannot be imaged directly because it is too small and distant, its presence is inferred from all these signals. Spectra show its temperature profile. Timing studies show its variability. Fluorescent lines show relativistic effects. Theoretical models of disk structure reproduce the observed data, confirming the interpretation. The unseen black hole is therefore revealed through the light of the disk, which acts as both a physical engine and a diagnostic tool. The accretion disk in this system demonstrates how matter and gravity combine to produce phenomena far beyond the power of normal stars. A wind from a massive star, captured and organized by the gravity of a compact object, becomes a continuous source of high-energy light. In this single structure, theories of stellar evolution, plasma physics, and general relativity intersect. The disk is both the consequence of a binary partnership and the signpost of a black hole, a place where ordinary gas meets the curvature of space-time and is transformed into radiation observable across the galaxy. The visible blue supergiant star in this binary system, Henry Draper Catalogue, number 226,196, provides not only a luminous companion to the unseen object, but also the key to measuring the compact companion's properties. Through optical spectroscopy, astronomers separate the light from this star into its component wavelengths. Within the spectrum, absorption lines appear where atoms in the star's atmosphere absorb specific energies of light. These lines are precise markers that shift when the star moves toward or away from Earth, an effect known as the Doppler shift. By recording these shifts across many nights, astronomers construct the velocity curve of the star. The result is a sinusoidal pattern repeating with a period of about 5½ days, the orbital period of the binary. This velocity curve shows that the blue supergiant moves alternately toward and away from Earth, proving that it is orbiting a massive unseen partner. The size of the shifts corresponds to orbital speeds of tens of kilometers per second. Combining these speeds with the orbital period allows astronomers to calculate the mass function, a relation that links the masses of both objects and the inclination of the orbit. The mass function provides a lower limit on the mass of the compact object. Even without precise knowledge of inclination, the minimum derived mass exceeds 3 solar masses which is above the maximum theoretical mass for a neutron star. This immediately suggests that the compact object must be a black hole. The spectral type of the blue supergiant also helps refine calculations. As an O 9.7 Eab star, it is expected to have a mass between 20 and 40 solar masses. The brightness of the star, combined with its spectral classification and distance, confirms this estimate. If the visible star is this massive, then the orbital dynamics require that the compact companion have a mass of 15 to 20 solar masses. This value is secure regardless of moderate uncertainties in inclination. Such a mass cannot be supported by any known state of matter other than a black hole, making the conclusion unavoidable. Optical spectroscopy also reveals additional features related to the stellar wind. The blue supergiant expels material that produces broad and sometimes asymmetric line profiles. These wind features vary as clumps pass across the line of sight, adding complexity to the velocity measurements. Careful analysis is required to separate the orbital Doppler shifts from wind-induced distortions. By modelling both effects, astronomers isolate the true motion of the star. The resulting velocity curve is consistent across decades of observation, reinforcing confidence in the orbital solution. Photometry. The measurement of brightness adds another layer of information. The gravitational pull of the compact companion distorts the shape of the blue supergiant, stretching it slightly along the line of centers. As the star rotates around the orbit, its projected area changes, producing small variations in brightness known as ellipsoidal variations. These variations follow the orbital period and provide clues to the inclination of the orbit. Higher inclinations produce stronger variations. By fitting models to the light curve, astronomers constrain the tilt of the system, narrowing the possible mass range of the black hole. Polarization studies provide yet another constraint. Light scattered in the stellar wind, and the accretion disk becomes polarized, meaning its electric field is preferentially aligned. The degree and angle of polarization vary as the binary orbits. These changes encode information about the geometry of the system, including the orientation of the orbital plane. Polarimetric measurements in both optical and X-ray bands support an inclination that, when combined with velocity, data yields a black hole mass near 20 solar masses. This convergence of methods demonstrates the strength of multi-technique analysis. Spectroscopy also captures occasional emission lines, produced when gas near the compact object is ionized by X-rays and then recombines. These lines provide evidence of interactions between the accretion flow and the stellar wind. Their strength and shape change with orbital phase, allowing astronomers to map the distribution of ionized gas. In some phases, the line of sight passes through denser parts of the wind, producing stronger absorption. In others, it passes through clearer regions. This variability helps reconstruct the three-dimensional structure of the wind, which is essential for understanding how matter is supplied to the black hole. The precision of modern instruments has refined all of these measurements. Large optical telescopes with sensitive spectrographs can detect velocity shifts of just a few kilometers per second. Applied to the blue supergiant, these instruments confirm the orbital parameters with remarkable accuracy. The consistency of results across observatories worldwide shows that the system is stable and well-defined. Each new generation of data tightens the constraints on the compact companion's mass. The convergence on a value too high for a neutron star is one of the strongest arguments that the companion is a black hole. This method of studying a visible star to infer the properties of an unseen companion has become standard in astrophysics. It is applied not only to black hole binaries but also to systems containing exoplanets and brown dwarfs. In every case, the motion of the visible object carries the gravitational imprint of the hidden one. Cygnus X-1 was the first example. where this method provided convincing evidence for a black hole, making it a landmark in the field. The lessons learned from its study continue to guide the analysis of other systems. By combining spectroscopy, photometry, and polarization, astronomers have built a detailed picture of this binary. The visible star moves in a 5.5-day orbit, its spectrum shifting back and forth in perfect rhythm. Its light curves show subtle variations caused by tidal distortion. Its wind produces absorption and emission features that interact with X-rays. All of these data points converge on the same conclusion: the unseen companion is massive, compact, and consistent only with a black hole. Through the light of a luminous blue star, the presence of a dark and invisible object is revealed with clarity. Determining the exact mass of the compact companion in this binary system has been one of the central achievements of observational astrophysics. The method begins with the radial velocity curve of the blue supergiant Henry Draper catalogue, number 226,196, derived from shifts in its absorption lines. The orbital period is about 5.5 days, and the amplitude of the velocity changes is around 75 kilometers per second. From these values, astronomers compute the mass function, which gives a minimum mass for the unseen object. The mass function depends only on observable quantities and provides a secure lower bound regardless of uncertainties in inclination. For this system, the mass function demands a compact object heavier than 4 times the mass of the Sun, already above the theoretical maximum for a neutron star. Refining this minimum requires estimating the inclination of the orbit and the mass of the blue supergiant. Inclination can be constrained by ellipsoidal variations in brightness, by polarization studies, and by the absence of eclipses in the light curve. These methods indicate that the orbit is inclined at a moderate angle, neither edge-on nor face-on. The mass of the blue supergiant is estimated from stellar evolution models, consistent with its spectral type O, 9.7 IAB and luminosity. Taken together, these factors yield a compact object mass of about 15 to 20 times that of the Sun. This range is well beyond the neutron star limit and firmly identifies the object as a black hole. Distance measurements provide another layer of certainty. Using very long baseline interferometry, astronomers have measured the trigonometric parallax of the system, fixing the distance at around 6,070 light-years. With this distance, the luminosity of the blue supergiant can be calculated, directly confirming its high mass. The X-ray luminosity is also calibrated consistent with the accretion of gas onto a black hole of the estimated size. Distant stellar models and orbital dynamics all converge on the same conclusion, reducing the possibility of error. Early debates questioned whether the compact companion could be a neutron star. Critics pointed out that if the orbital inclination were closer to face, the true mass could be lower. However, polarization and photometric data ruled out such a low inclination. Others speculated about exotic forms of matter such as quark stars that might support higher masses. Yet theoretical models show that even such exotic stars cannot exceed 4 to 5 solar masses without collapsing. The mass of 15 to 20 solar masses is far above any plausible alternative. By the late 1970s, consensus formed that the companion was a black hole. The measurement of such a mass also sheds light on the system's history. For a black hole of this size to form its progenitor star must have been extremely massive, perhaps 50 or 60 solar masses. Such a star would have exhausted its fuel, quickly collapsed, and either exploded in a supernova or imploded directly into a black hole. The binary remained intact, meaning that the collapse did not impart a large kick that would have disrupted the system. This suggests that the black hole may have formed through direct collapse rather than through a violent explosion. The relatively low proper motion of the system supports this scenario. The accuracy of mass measurements has improved over time. In the 1970s, uncertainties were large, and the black hole's mass was only roughly estimated. With modern spectrographs on large telescopes, radial velocities are measured with precision of a few kilometers per second. Long-term monitoring has refined the orbital parameters, removing ambiguities. Parallax measurements with radio interferometry have pinned down the distance with errors of only a few percent. With these advances, the mass of the black hole in this system is now one of the best measured among stellar mass black holes in the Milky Way. The importance of this measurement goes beyond this single system. It provides a benchmark for theories of stellar evolution and black hole formation. Models must explain how a black hole of 20 solar masses can form in a binary without disrupting its companion. The existence of such a system validates the idea that very massive stars can collapse quietly, leaving black holes without supernova explosions. This in turn helps explain the population of massive black holes detected through gravitational waves, which often show masses in the range of 20 to 30 solar masses. The mass of the companion in this binary was the first evidence that such heavy stellar mass black holes exist. Mass measurement also lays the foundation for other studies. To estimate the spin of a black hole from X-ray spectra, one must first know its mass. To model the accretion flow and its efficiency, mass must be fixed. To interpret timing, features such as quasi-periodic oscillations, mass provides the scaling of orbital frequencies. In all of these areas, the secure measurement of 15 to 20 solar masses for the black hole gives confidence that models are grounded in reality. Without a reliable mass, conclusions about spin accretion physics or jet production would be uncertain. The techniques used here have become standard for identifying black holes in other binaries. Astronomers first identify an X-ray source, then locate its optical counterpart. They measure the spectrum of the visible star track, its velocity curve, compute the mass function, and refine the result with estimates of inclination and stellar mass. This process, pioneered with this system, is now routine. Dozens of black hole binaries have been identified this way, but this system remains the classic case where the method was first proven. Its role in establishing the methodology is as significant as its role in proving that black holes exist. The mass of the compact object in this binary therefore represents more than a number. It is the culmination of decades of observation, analysis, and refinement. It demonstrates how invisible objects can be weighed through the motions of their companions. It validates the predictions of stellar evolution and general relativity. It shows that black holes are not only possible, but real, with measurable properties. The heavy companion of Henry Draper Catalogue number 226,196 is the first black hole to be accepted on the basis of mass measurement, setting the standard for all subsequent discoveries. The theory of general relativity provides the framework for interpreting the nature of the compact object in this binary system. According to Albert Einstein's equations, mass and energy curves, space-time and objects move along paths defined by this curvature. If enough mass is concentrated into a sufficiently small volume, space-time becomes so curved that no path allows escape. The boundary of this region is called the event horizon. Inside the event horizon, all trajectories lead inevitably toward the center. Light itself cannot emerge. For an observer far away, the black hole is marked by this invisible horizon, a surface from which no information can return. The compact object in this system has a mass of about 15 to 20 times that of the Sun. The Schwarzschild radius, which is the event horizon radius for a non-rotating black hole, is about 3 kilometers for each solar mass. Thus, the radius of this object's event horizon is between 45 and 60 kilometers. By comparison, the Sun's radius is about 700,000 kilometers. The contrast shows how dense the black hole must be. The mass of 20 suns compressed into a region no larger than a small city. The surrounding blue supergiant has a radius of about 20 solar radii, which is millions of kilometers across, making the size difference between the two objects extreme. General relativity also predicts the existence of the innermost stable circular orbit, the smallest orbit in which matter can circle a black hole without spiraling inward. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. If the black hole spins, the orbit moves closer to the event horizon. For a rapidly spinning black hole, it can lie just above the horizon. This innermost orbit is significant because it sets the maximum efficiency of accretion. Gas that spirals in releases gravitational energy until it reaches this orbit, then plunges inward rapidly. The location of this boundary influences the temperature of the accretion disk and the shape of the X-ray spectrum. Light emitted near the black hole experiences strong gravitational redshift. Photons climbing out of the deep gravitational well lose energy, stretching to longer wavelengths. This effect is visible in the broad iron K-alpha line observed in the system's X-ray spectrum. The line, normally sharp at a specific energy, appears broadened and asymmetric. Part of the broadening comes from Doppler shifts caused by the rapid orbital motion of gas in the disk, while the long red wing of the line is caused by gravitational redshift. Together, these features confirm that matter orbits very close to the event horizon where relativity governs the behavior of light. Another consequence of relativity is the dilation of time in strong gravitational fields. Near the event horizon, time passes more slowly relative to a distant observer. Although this cannot be directly experienced, it affects how variability is observed. Fluctuations in the X-ray emission correspond to processes occurring within the inner disk. The timescales of these fluctuations match the orbital periods, predicted by relativity at radii only a few times the Schwarzschild radius. Millisecond variations indicate that matter is orbiting at tens of thousands of kilometers per second close to the speed of light. These observations align with theoretical expectations and support the conclusion that the compact object is a black hole. If the black hole is spinning, its geometry is described by the Kerr solution of general relativity. In this geometry, space-time itself is dragged around by the rotating mass, an effect called frame dragging. The region outside the event horizon where this occurs is called the ergosphere. Within the ergosphere, objects cannot remain at rest relative to distant observers, but must rotate with the black hole. Theoretical models suggest that energy can be extracted from the spin of a black hole through processes such as the Penrose mechanism or the Blanford-Zanarczyk mechanism, which involves magnetic fields. These ideas are important for understanding how jets might be launched from accreting black holes. Observations of faint radio jets in this system raise the possibility that spin energy contributes to outflows, although the details remain uncertain. The absence of a solid surface is another hallmark of a black hole. If the compact object had a surface, gas falling onto it would collide and produce bursts of radiation. Instead, the radiation from this system matches the gradual release of energy in an accretion disk with no final impact. Gas spirals inward, radiates and disappears across the horizon without a visible burst. This absence of surface emission is indirect but persuasive evidence that the compact object has an event horizon. Gravitational lensing, another prediction of relativity, also plays a role. Light emitted from the inner disk is bent by the curvature of space-time around the black hole. Some photons circle the black hole before escaping, arriving later, and contributing to the broadening of spectral features. Lensing enhances the flux from some regions of the disk, while dimming others, creating the asymmetry seen in observed spectra. Modeling these effects allows astronomers to map the structure of the disk and test predictions of relativity in strong fields. Theoretical models and simulations support these interpretations. Magneto-hydrodynamic simulations of accretion disks around spinning black holes reproduce the broad iron line, the variability and the state transitions observed. They show that turbulence, magnetic reconnection, and relativistic orbital motion combine to produce the rich phenomenology of systems like this one. When compared with data, these simulations provide confidence that general relativity correctly describes the physics near the event horizon. Relativity not only explains the observations, but also guides future measurements. The spin of the black hole remains an area of active study because spin affects the position of the innermost stable orbit and the shape of the X-ray spectrum. Measuring spin tests both models of stellar evolution and the predictions of relativity. Polarization, now measurable with new instruments, provides another test. Relativity predicts that light near the black hole should be polarized in specific ways by scattering and lensing. Detecting and modeling this polarization adds another layer of evidence. This binary system therefore serves as a natural laboratory for testing general relativity under conditions impossible to reproduce on Earth. The compact object's mass and size place it in the regime of strong gravity where relativistic effects dominate. The accretion disk provides light that interacts with curved space-time, revealing redshift, broadening, and time dilation. Each observation fits the theoretical predictions, strengthening the conclusion that the unseen companion is a black hole. When the system in Cygnus was first identified as a candidate for hosting a black hole, the claim was met with caution. In the early 1970s, the concept of a black hole was still considered speculative by many astronomers. The equations of general relativity predicted them, but their existence in the real universe had not been firmly demonstrated. Some researchers argued that the compact companion might instead be a neutron star or some other form of exotic matter. The debates that followed highlight the scientific process where evidence is scrutinized, alternatives are considered, and consensus forms only when no other explanation can account for the data. The first argument raised against the black hole interpretation concerned the orbital inclination. If the system were being observed at a shallow angle nearly face-on, the true orbital velocities would be smaller than the measured radial component. This would reduce the inferred mass of the compact object, potentially bringing it within the range of a neutron star. For several years, this possibility was seriously discussed. However, as more data were gathered, especially from photometric variations and polarization studies, the inclination was constrained more tightly. The results consistently showed that the inclination was moderate, not face-on. The mass estimates for the compact object remained above the neutron star limit, closing off this escape route for alternative interpretations. Another line of skepticism focused on the nature of neutron stars themselves. In the early 70s, the maximum possible mass of a neutron star was not well defined. Some theorists suggested that neutron stars could be heavier than 3 solar masses, depending on the equation of state of nuclear matter at extreme densities. If this were true, then the compact object in this system might be a neutron star after all. Over time, however, advances in nuclear physics and observations of pulsars constrained the maximum neutron star mass to about 2.5 solar masses. With this limit accepted, the companion's mass of 15 to 20 solar masses clearly lay beyond it. The neutron star hypothesis was eliminated. Some researchers proposed exotic alternatives such as quark stars, boson stars, or other hypothetical states of ultra-dense matter. These ideas arose from theoretical explorations of high-energy physics and attempted to find middle ground between neutron stars and black holes. Yet none of these models could support masses anywhere near 15 to 20 solar masses, without collapsing into a black hole. The data therefore provided no support for such alternatives. They remained interesting theoretical constructs, but not viable explanations for this binary. The variability of the X-ray emission also played a role in the debate. Some argued that the rapid flickering might be produced by instabilities in the stellar wind rather than by accretion onto a compact object. However, the sub-second timescales of the fluctuations implied an emission region, only a few hundred kilometers across. Stellar winds are far too large and diffuse to vary on such short timescales. Only a compact object could account for the observations. The variability therefore strengthened the case for a black hole rather than weakening it. The most persuasive evidence came from the convergence of multiple lines of data. The mass function, the spectral classification of the blue supergiant, the inclination derived from light curves and the distance measured by parallax all pointed to the same conclusion. The unseen companion had a mass well above the neutron star limit. Its radiation emerged from a region far smaller than any normal star. The shape of the iron K-alpha line matched predictions for relativistic broadening near a black hole. Each independent measure reinforced the others. Together they formed a coherent picture that left little room for doubt. As the evidence accumulated, the tone of the debate shifted. By the late 1970s, most of the astrophysical community accepted that this system contained a black hole. A few dissenters remained, but their objections grew increasingly speculative as the data became stronger. The case of this binary was the first where the balance of evidence convinced the majority that a stellar mass black hole had been observed. In this way, it marked the transition of black holes from theory to reality in the minds of working scientists. The debates also had value beyond the specific case. They spurred the refinement of methods for measuring masses, constraining inclinations, and modeling accretion disks. The scrutiny applied to the data ensured that the conclusion was robust. Once the alternative explanations were exhausted, the acceptance of the black hole interpretation carried more weight because it had survived serious challenge. This episode illustrates how science advances through skepticism, evidence, and eventual consensus. The public reception of the discovery added another dimension. News that a black hole might exist in the constellation Cygnus captured the imagination of the press and the public. Headlines proclaimed the discovery of a cosmic vacuum cleaner or an invisible monster star. While these descriptions were exaggerated, they helped introduce the concept of black holes to a broader audience. At the same time, scientists emphasized the cautious nature of their conclusions, distinguishing between what was certain and what remained tentative. The balance between public interest and scientific precision was delicate, but the attention ensured that black holes became part of popular culture as well as astrophysics. As decades passed and instruments improved, the debates faded. Modern measurements of distance, mass, and spin leave no doubt about the nature of the compact companion. Yet the history of skepticism remains important. It shows that extraordinary claims require extraordinary evidence, and that the burden of proof lies with those proposing the existence of an entirely new class of object. In this case, the evidence was found, tested, and confirmed. The system in Cygnus became the first black hole widely accepted by the scientific community, not because the idea was fashionable, but because no other explanation survived scrutiny. The debates of the 1970s thus occupy an important chapter in astrophysics. They represent the moment when black holes became more than equations and entered the realm of observed phenomena. They also represent the way scientific knowledge grows through challenge, debate, refinement, and resolution. The binary system in Cygnus was the stage for this process, and the outcome reshaped the study of high-energy astrophysics for decades to come. The brightness of the X-ray source in this binary is not constant, but varies rapidly, sometimes within fractions of a second. Such rapid variability is a hallmark of accretion onto a compact object and provides insight into the size and structure of the region where radiation is produced. In astrophysics, the timescale of variation sets an upper limit on the dimensions of the emitting zone. If the flux changes within 1/10 of a second, then the source must be smaller than the distance light travels in that time, which is about 30,000 kilometers. This size constraint is only a few times larger than the radius of the event horizon of a black hole, with a mass of 15 to 20 suns, confirming that the X-rays originate in the innermost regions of the accretion flow. The variability appears on many timescales. On the shortest scales, fluctuations lasting milliseconds point to turbulence and instabilities in the plasma. These variations may arise from magnetic reconnection, where twisted field lines snap and release energy suddenly. On longer scales of seconds to minutes, quasi-periodic oscillations emerge, repeating signals at specific frequencies. These are thought to correspond to resonances in the disk where orbital motion and oscillatory modes interact. Some may be linked to orbital frequencies near the innermost stable circular orbit predicted by general relativity. Because these frequencies depend on the mass and spin of the black hole, they provide indirect probes of those parameters. Variations also occur on hours to days. These are influenced by the stellar wind of Henry Draper, catalogue number 226,196. The wind is not smooth but clumpy, and as clumps pass into the line of sight or feed, the accretion flow, the X-ray brightness responds. Sometimes absorption dips occur when dense regions block the radiation. At other times, enhanced accretion produces flares. This irregular feeding process explains why the system never shines with perfect steadiness. The variability is a natural consequence of wind-fed accretion in a high-mass binary. Detecting and analyzing these changes requires instruments with high time resolution. Early satellites such as Uhuru showed that the source was variable, but it was the Rossi X-ray Timing Explorer launched in 1995 that transformed the field. Its detectors could measure the arrival times of individual photons with microsecond precision. Applied to this system, they revealed a complex power spectrum of variability with broad noise components, quasi-periodic oscillations, and energy-dependent lags. These patterns match predictions from models of accretion flows governed by magnetohydrodynamic turbulence and relativistic orbital motion. One key finding is that the strength of variability depends on energy. Hard X-rays produced in the corona fluctuate more strongly than soft X-rays from the disk. This suggests that the corona is highly dynamic with rapid changes in temperature and density. Soft X-rays vary more smoothly, consistent with emission from the broader, more stable disk. Time lags between energy bands provide further clues. Often variations in hard X-rays precede those in soft X-rays by fractions of a second, consistent with fluctuations in the corona affecting the disk, or with photons scattering multiple times before escaping. Measuring these lags provides a way to map distances within the inner regions of the system. The variability also depends on the spectral state. In the low hard state, when the corona dominates, the source shows strong rapid fluctuations and pronounced quasi-periodic oscillations. In the high soft state, when the disk dominates, the emission is steadier and the power at high frequencies is reduced. These state-dependent patterns are consistent with changes in the geometry of the accretion flow. In the hard state, the corona is extended and variable. In the soft state, the disk extends inward to the innermost stable orbit, leaving less room for coronal activity. Tracking these transitions provides insight into how matter organizes itself around a black hole. Quasi-periodic oscillations are particularly important because they may correspond to characteristic frequencies of orbital motion near the black hole. For example, the nodal precession of tilted orbits predicted by the lens-Thirring effect of general relativity could produce low-frequency oscillations. Higher frequency oscillations may correspond to orbital and epicyclic motions at the inner disk edge. If these identifications are correct, then quasi-periodic oscillations provide a direct test of relativity and strong gravity. In this system, oscillations at frequencies of a few hertz to tens of hertz have been detected matching the expected range for a black hole of 20 solar masses. Long-term monitoring has revealed that variability patterns change with time, sometimes gradually and sometimes abruptly. These changes likely reflect shifts in accretion rate, magnetic field configuration and wind structure. The system therefore offers a dynamic laboratory where the interplay of plasma physics and gravity can be observed directly. No single model explains all features, but the broad agreement between simulations and data supports the view that magnetohydrodynamic turbulence in a relativistic disk produces the observed signals. Another aspect of variability is the correlation between X-rays and other wavelengths. Radio emission from the jet is stronger when the system is in the low hard state, the same state with strong X-ray variability. This correlation suggests that the processes driving variability in the corona are linked to jet production. Infrared and optical emission also show flickering correlated with X-rays, implying that some of the variable radiation is reprocessed by the outer disk or by the surface of the blue supergiant. These multi-wavelength connections demonstrate that variability is not confined to the inner disk, but propagates through the entire system. From the earliest detections of flickering to the detailed timing studies of recent decades, variability has been one of the strongest indicators that the compact companion is a black hole. No ordinary star could change brightness so quickly. The only objects with regions small enough and deep gravitational wells strong enough are neutron stars or black holes. With the mass of the companion far above the neutron star limit, the conclusion is secure. The fluctuations in brightness are not just noise, they are the direct signature of gas swirling near the event horizon of a black hole. The study of variability has moved from simple detection to quantitative probes of accretion physics and relativity. Every flicker and oscillation is a clue to the behavior of matter in curved space-time. By dissecting the patterns of variability, astronomers measure distances, map flows, and test theories. The system in Cygnus, with its persistent brightness and strong variability, has been central to this progress. It remains one of the best observed examples of how timing reveals the nature of black holes. Understanding this binary system requires not only the study of X-rays but also observations across the entire electromagnetic spectrum. Each wavelength provides different information about the components and processes at work. Optical light reveals the visible supergiant star ultraviolet, traces the hot outer layers of the star's atmosphere, and the effects of ionization. Infrared records emission from dust and cooler gas, and radio uncovers evidence of outflows and possible jets. Together, these observations create a multi-wavelength picture that is far richer than any single band of data could provide. Optical spectroscopy remains central because it gives direct evidence of the orbital motion of Henry Draper Catalogue number 226,196. The Doppler shifts of absorption lines trace the star's velocity, while photometric variations show how its shape is distorted by the gravity of the compact companion. The light curve reveals subtle ellipsoidal variations synchronized with the orbital period, confirming the gravitational interaction between the two bodies. Polarimetric observations add to this picture by measuring changes in the alignment of light waves as they scatter in the stellar wind and accretion environment, further constraining the geometry of the orbit. Ultraviolet observations from satellites such as the International Ultraviolet Explorer and the Hubble Space Telescope probe the star's wind in detail. Absorption lines from ionized carbon, nitrogen, and oxygen reveal the velocity and density of the outflow. These lines vary as the binary orbits, showing how the compact companion's X-rays ionize different regions of the wind. The data demonstrate that the wind is clumpy and structured rather than smooth. These clumps influence the accretion process, sometimes increasing and sometimes decreasing the flow of material into the disk. Monitoring ultraviolet spectra over many orbital cycles has provided maps of the wind's structure, helping astronomers model the feeding of the black hole. Infrared data add another layer of information. While the blue supergiant dominates in visible and ultraviolet light, the infrared band can isolate contributions from dust and cooler gas in the environment. Observations with the Spitzer Space Telescope and ground-based infrared instruments have revealed emission from circumstellar material and helped refine the distance to the system. Infrared interferometry with facilities such as the Very Large Telescope Interferometer has even resolved the distorted shape of the blue supergiant, confirming the tidal influence of the compact companion. These data link the immediate environment of the binary with the larger scale structures formed by the interaction of stellar wind and interstellar medium. Radio observations provide evidence for jets and outflows. This system has been detected as a steady but faint radio source. With very long baseline interferometry, astronomers have imaged elongated features extending from the central source, consistent with a jet moving at relativistic speeds. The radio emission is stronger when the system is in the low hard state, the same state where the corona dominates in X-rays. This correlation suggests a link between processes in the corona and the launching of jets. Although the jets are weaker than in some other systems, their detection demonstrates that even a classical black hole binary can produce outflows that extend far beyond the accretion disk. Multi-wavelength monitoring has shown how emission in different bands is correlated. X-ray flares are sometimes followed by optical or infrared echoes, as high-energy photons strike the outer disk or the surface of the star and are reprocessed into lower-energy light. Radio brightness rises during periods of strong X-ray variability reflecting changes in the jet. These correlations reveal the flow of energy through the system from the innermost regions of the accretion disk out to the environment tens of millions of kilometers away. They show that the binary is not a collection of independent components, but a tightly coupled system where disk, corona, wind, and jet interact continuously. The synergy of observations across wavelengths also strengthens the case for a black hole. Optical spectroscopy measures the orbit and mass function. Ultraviolet data confirm the influence of intense X-ray radiation on the wind. Infrared and radio observations show structures that extend beyond the immediate binary, shaped by outflows from the compact object. All of these elements align with the interpretation of a black hole accreting matter from a massive companion. No alternative model explains the full set of data across the spectrum. The technology enabling these observations has advanced steadily. Early optical spectroscopy could measure velocities with uncertainties of tens of kilometers per second. Modern instruments achieve precision of just a few kilometers per second. Ultraviolet observations were impossible before space telescopes but are now routine. Infrared interferometry can resolve angular scales previously thought unreachable. Radio interferometry can measure positions with millisecond precision, allowing the parallax distance to be determined with unprecedented accuracy. Each improvement has added detail to the portrait of this system, refining earlier conclusions and reducing uncertainties. These multi-wavelength studies also provide context within the galaxy. At a distance of about 6,000 light-years, the system lies in the Orion Arm, a region of active star formation. the surrounding interstellar medium bears evidence of energy input from the binary, including bow shocks and ionized regions. These structures show that the influence of the system extends far beyond the orbit of the two stars. The energy released by accretion and outflows shapes the surrounding gas, linking the fate of the binary to the evolution of its galactic environment. The lessons drawn from this system apply to others. By demonstrating how multi-wavelength observations converge on a consistent model, it has provided a template for studying black hole binaries elsewhere. Many subsequent discoveries have followed the same path identification of an X-ray source association with an optical star measurement of orbital motion and confirmation through data in ultraviolet, infrared, and radio. The first example became the model, and its continued observation ensures that methods are tested and improved. The binary in Cygnus is therefore not only a unique case, but also a representative of a class. It shows how the visible and the invisible combine to create phenomena observable across the spectrum. It demonstrates that no single wavelength is sufficient, but that the integration of all data builds a coherent picture. From optical to X-rays, from infrared to radio, the system reveals itself piece by piece. Each observation illuminates a different layer of the structure, and together they reveal the reality of a black hole fed by the wind of a massive star. The binary system in Cygnus does not only attract matter inward, it also produces outflows that carry matter and energy back into space. These outflows occur on multiple scales and in different forms. The stellar wind of Henry Draper Catalogue, number 226,196, is one outflow driven outward by radiation pressure from the hot star. The accretion disk itself may also produce a disk wind where gas is expelled by radiation or magnetic forces before it can reach the event horizon. In addition, the system shows evidence for jets, narrow beams of particles, accelerated to relativistic speeds, and detected through faint but steady radio emission. Together, these outflows demonstrate that accretion is not a one-way process but a balance of inflow and release. The stellar wind dominates the mass transfer into the system. Gas flows outward from the surface of the blue supergiant at thousands of kilometers per second. Some fraction of this gas is captured by the compact object, but much continues outward, carrying angular momentum and energy into the interstellar medium. The wind is structured and clumpy, as shown by variability in ultraviolet absorption lines and by dips in the X-ray light curve. These clumps sometimes reduce the accretion rate and sometimes enhance it depending on their trajectories. They also absorb radiation, shaping the observed spectra. The stellar wind thus plays a dual role, both feeding and regulating the black hole's accretion. Disk winds are more subtle but still important. High-resolution X-ray spectra obtained by the Chandra X-ray Observatory have revealed absorption features from highly ionized iron and other elements moving outward at hundreds of kilometers per second. These features are interpreted as signatures of gas being driven from the disk by radiation pressure or by magnetic forces. Such winds remove mass angular momentum and energy from the accretion flow, reducing the rate at which gas reaches the inner disk. They may also affect the state transitions of the system, with stronger winds associated with softer states. In this way, disk winds add another layer of complexity to the feedback between the compact object and its environment. Jets provide the most dramatic form of outflow. Although weaker than those seen in some other microquasars, the jets in this system are still significant. They are detected through steady radio emission that strengthens when the system is in the low hard state. Very long baseline interferometry has imaged elongated structures extending from the central source consistent with the collimated jet. The emission is non-thermal, produced by synchrotron radiation, as relativistic electrons spiral along magnetic field lines. The jets carry energy and particles away from the vicinity of the black hole, transporting a fraction of the accreted matter outward at nearly the speed of light. The launching of jets is thought to involve the interaction of magnetic fields with the rotating accretion disk, and possibly with the spin of the black hole itself. The Blanford-Znayak mechanism describes how magnetic fields threading the ergosphere of a spinning black hole can extract rotational energy and channel it into a jet. Alternatively, the Blanford-Payne mechanism describes how magnetic fields anchored in the disk can fling gas outward along open field lines. Both mechanisms may operate with a relative importance depending on the configuration of the magnetic field and the spin of the black hole. The presence of jets in this system suggests that such processes occur even when the outflows are relatively weak. The energy carried by the jets is modest compared to the X-ray luminosity of the accretion disk, but over long timescales it is significant. Radio observations of the environment around the system reveal large-scale structures including bow shocks and bubbles of ionized gas that appear to have been shaped by the jets and winds. These features show that the system influences its surroundings on parsec scales, injecting energy into the interstellar medium. In this way, the binary acts not only as a source of radiation, but also as an engine of galactic ecology, stirring and heating the gas between stars. The coupling between inflow and outflow is evident in the correlations between X-ray and radio emission. In the low hard state, when the corona is strong and variability is high, the radio jet is also present. In the high soft state, when the disk dominates and the corona weakens, the radio emission diminishes. This pattern suggests that the corona and the jet are connected, perhaps with the jet forming at the base of the corona. Changes in accretion geometry therefore affect both the inner disk and the larger scale outflows. Simulations of magnetohydrodynamics around black holes reproduce many of these features. They show how magnetic fields can channel inflowing gas into outflows, creating both disk winds and jets. The balance between inflow and outflow depends on the accretion rate, the spin of the black hole, and the structure of the magnetic field. Observations of this system match these predictions, lending support to the theoretical models. At the same time, the details of jet launching remain uncertain, and ongoing observations aim to refine the picture. The existence of multiple outflow channels complicates the energy budget of the system. Not all of the mass lost by the blue supergiant reaches the event horizon. Some fraction is expelled in disk winds and some is redirected into jets. This means that the growth of the black hole is slower than the inflow rate might suggest. At the same time, the surrounding environment is enriched and energized by the expelled matter. The binary is therefore not only a sink of mass and energy, but also a source of feedback into the galaxy. Studying outflows in this system also informs the broader context of black hole astrophysics. Jets and winds are seen from stellar mass black holes, neutron stars, and supermassive black holes in galactic nuclei. The similarities suggest that the processes are universal scaling with mass and accretion rate. By observing a nearby system in detail, astronomers gain insight into mechanisms that operate on much larger scales in distant galaxies. This system thus serves as a bridge between stellar and galactic black hole phenomena. The evidence for stellar winds, disk winds, and jets in this binary underscores the complexity of accretion. Matter does not simply fall inward. It circulates, interacts, and escapes in multiple directions. Outflows are as essential to the story as inflows. They regulate accretion, shape the environment, and link small scales near the event horizon with large scales in the galaxy. The system in Cygnus provides a vivid example of this balance, making it an essential laboratory for understanding how black holes interact with their surroundings. One of the most important achievements in the study of this binary system has been the precise determination of its distance. Without knowing how far away an object lies, its true luminosity, mass, and scale remain uncertain. Early estimates of the distance to the source varied widely from about 2,000 to more than 7,000 light-years. These estimates were based on indirect methods such as comparing the apparent brightness of the blue supergiant Henry Draper, catalogue number 226,196, with models of its spectral type. The large uncertainties in distance meant that astronomers could not be certain of the system's absolute properties. This situation changed with the application of very long baseline interferometry, a technique that links radio telescopes separated by thousands of kilometers into a single instrument with extremely high resolution. By measuring the parallax of the source, the tiny apparent shift in its position as Earth orbits the Sun, astronomers obtained direct geometric distance. In 2011, a team used this method to determine that the binary lies about 6,070 light-years from Earth, with an uncertainty of only a few %. This measurement transformed the study of the system by anchoring its physical parameters to a secure scale. With the distance fixed, the luminosity of the blue supergiant could be calculated accurately. Its observed brightness in visible light combined with the distance corresponds to a true luminosity of hundreds of thousands of times that of the Sun. This value agrees with expectations for a star of its spectral type 09.7 IAB. From this luminosity and temperature, the radius of the star is derived as about 20 times solar, and its mass is constrained to between 20 and 40 solar masses. These values confirm the star's identity as a massive supergiant in an advanced stage of evolution. The X-ray luminosity of the system can also be calibrated with the distance. The observed flux at Earth translates to a total energy output in X-rays of about 100,000 solar luminosities. This extraordinary power arises from accretion onto the compact companion and matches theoretical expectations for a black hole of 15 to 20 solar masses. The consistency between the observed luminosity, the estimated accretion rate from the stellar wind, and the predictions of accretion theory reinforces the interpretation of the compact object as a black hole. Precise distance also informs the measurement of orbital parameters. When the star's radial velocity curve is combined with the distance, astronomers can better estimate the inclination of the orbit. This reduces uncertainties in the derived mass of the compact object. The improved measurements confirm that the companion's mass is too high to be a neutron star. The mass is securely in the range of 15 to 20 solar masses, leaving a black hole as the only viable explanation. In addition to parallax, very long baseline interferometry has measured the proper motion of the system across the sky. By combining this with radial velocity measurements, the full three-dimensional velocity of the binary through the galaxy is obtained. The velocity is modest, suggesting that the black hole did not receive a strong kick when it formed. Some black holes are ejected at high speeds due to asymmetric supernova explosions. In contrast, the gentle motion of this system implies that the black hole may have formed through direct collapse of a massive star without a violent explosion. This conclusion has significant implications for models of black hole formation and the fate of massive stars. The distance also places the system in its galactic context. At about 6,000 light-years, it lies within the Orion arm of the Milky Way, a spiral arm rich in massive stars and star-forming regions. This location suggests that the binary formed in an environment of active stellar birth, where two massive stars could emerge together from the same molecular cloud. The evolutionary history implied by the current configuration is that both stars began as massive O-type stars. One evolved more quickly, exhausted its fuel, and collapsed into a black hole. The binary remained bound and the surviving star continued its evolution as the blue supergiant observed today. Another consequence of the precise distance is its impact on measurements of the black hole's spin. Methods for estimating spin from X-ray spectra depend on knowing the luminosity of the accretion disk. If the distance is uncertain, the luminosity is also uncertain, and spin estimates become unreliable. With the parallax distance established, spin measurements gain credibility. Current models suggest that the black hole in this system is rotating rapidly, perhaps near the maximum allowed by relativity. This rapid spin influences the efficiency of accretion and may contribute to the production of jets. The accurate distance has also clarified the evolutionary future of the system. With a mass of 20 to 40 solar masses, the blue supergiant will eventually end its life in a collapse of its core. Depending on details such as mass loss in winds, metallicity and rotation, it may form another black hole. If the binary remains bound after this event, the system would contain two black holes orbiting each other. Over billions of years, gravitational radiation would cause them to spiral together and merge. Such a merger would produce a burst of gravitational waves detectable by instruments like the Laser Interferometer Gravitational Wave Observatory. The system therefore provides a possible link between current X-ray binaries and the black hole mergers now observed through gravitational waves. The parallax distance measurement to this binary is considered a milestone in radio astronomy. Measuring a shift as small as 0.5 millisecond required linking telescopes across continents and correcting for atmospheric and instrumental effects with extreme precision. The success of the measurement not only anchored the properties of this particular system, but also demonstrated the power of very long baseline interferometry for mapping the galaxy. Other X-ray binaries have since been measured in the same way, expanding the catalogue of black holes with secured distances and masses. In summary, the determination of the distance to this system has provided the foundation for all subsequent conclusions. It fixed the luminosities of both the star and the X-ray source, confirmed the mass of the black hole, clarified the formation history and improved spin estimates. It connected the binary to its place in the Milky Way and to the broader questions of stellar evolution and gravitational wave sources. Without this precise distance, the system would still be remarkable. With it, the system has become one of the most important benchmarks in astrophysics, serving as a reference for the study of black holes across the universe. The continuous improvement of instruments over the past half-century has steadily sharpened the picture of this binary system. When Cygnus X-1 was first identified as a strong X-ray source in the early 1970s, detectors aboard satellites such as Uhuru and Ariel 5 could only measure crude fluxes and broad variability. Their data showed that the source was bright, persistent, and highly variable, but the spectral resolution was too poor to identify detailed features. As technology advanced, each new generation of instruments provided more precise information, allowing astronomers to test models of accretion, physics measure parameters of the black hole, and probe the structure of the surrounding environment. The Chandra X-ray Observatory, launched in 1999, brought high-resolution spectroscopy to the study of Cygnus X-1. Its gratings disperse X-rays into finely detailed spectra, revealing narrow absorption lines produced by the stellar wind of Henry Draper Catalogue number 226,196. These lines shift and vary with orbital phase, demonstrating how the black hole's radiation ionizes the wind and creates complex structures of hot gas. Chandra has also detected absorption features indicating the presence of outflowing material from the accretion disk, providing evidence of disk winds. The ability to distinguish such fine features has deepened the understanding of how inflow and outflow interact. XMM Newton, launched the same year, has complemented Chandra with its large collecting area, enabling precise measurements of broad spectral features. Its data on the iron K-alpha line have been central to determining the black hole's spin. This fluorescent line, produced when iron atoms are excited by X-rays, appears broadened and skewed in Cygnus X-1. The distortion matches the predictions of general relativity for emission from matter orbiting close to a black hole. By modelling the shape of the line, astronomers have inferred that the black hole is spinning rapidly, with an innermost stable orbit very close to the event horizon. This result links observation directly to the physics of curved space-time. NuSTAR, launched in 2012, extended the view into higher energy X-rays up to 80 kilo-electron-volts with focusing optics. For the first time, astronomers could measure the shape of the high-energy spectrum in detail. NuSTAR revealed that the corona, the region of hot electrons above the disk, is compact and close to the black hole. Its data confirmed that photons from the disk are scattered to higher energies through inverse Compton processes in the corona. By fitting models to the observed spectrum, researchers constrained both the spin of the black hole and the geometry of the corona. The results support the picture of a rapidly spinning black hole with a small dynamic corona. The Rossi X-ray Timing Explorer, which operated from 1995 to 2012, transformed the study of variability. With time resolution down to microseconds, it recorded light curves of Cygnus X-1 that revealed quasi-periodic oscillations and broad noise features across a wide range of frequencies. These timing signatures are interpreted as manifestations of orbital motion, disk turbulence, and relativistic effects near the event horizon. The data from Rossi remain a cornerstone of models that link observed variability to theoretical predictions of magnetohydrodynamics in curved space-time. The Imaging X-ray Polarimetry Explorer, launched in 2021, opened a new window by measuring the polarization of X-rays. For Cygnus X-1, it has detected polarization consistent with scattering in a flattened disk and a compact corona. Polarization provides geometric information independent of spectra and timing, helping to distinguish between models of the corona's shape. Early results suggest that the corona may be extended along the disk axis, possibly linking it to the base of the jet. This new dimension of data promises to refine the understanding of the system further. Beyond X-rays, large ground-based telescopes have contributed through high-precision optical spectroscopy. The Very Large Telescope in Chile, with its sensitive spectrographs, has measured the radial velocities of the blue supergiant with unprecedented accuracy, refining the orbital parameters. Interferometric instruments on the Very Large Telescope interferometer have resolved the distorted shape of the star, confirming tidal interactions with the black hole. These optical data reduce uncertainties in inclination and mass, reinforcing the conclusions drawn from X-ray observations. Radio astronomy has also played a crucial role. The Very Long Baseline Array has imaged elongated radio emission consistent with jets, while the Very Large Array has monitored long-term changes in flux. The parallax distance of 6,070 light-years was measured using very long baseline interferometry, anchoring all other physical measurements. These radio observations connect the small-scale processes near the black hole to structures extending across parsecs of interstellar medium. Spacecraft that monitor the sky continuously, such as Swift and Maxi on the International Space Station, have tracked the source over long timescales. Their data show how the system switches between spectral states from the low hard state dominated by coronal emission to the high soft state dominated by the disk. These transitions are accompanied by changes in radio emission and timing properties, Monitoring over decades has revealed that the system spends most of its time in the low hard state, but occasionally shifts into the high soft state, providing a natural laboratory for studying how accretion geometry changes. The integration of data from all these instruments has built one of the most complete portraits of any black hole binary. Distance mass, spin orbital parameters, disk structure, corona geometry, jet production, and wind interactions have all been measured. The system has become a benchmark for testing theories of accretion and relativity. Each new observation confirms the conclusion that the unseen companion is a black hole and adds detail to the mechanisms that govern its behavior. The progress made also illustrates how technology drives discovery. Without space-based X-ray detectors, the system would remain invisible in its most important band. Without interferometry, its distance would remain uncertain. Without sensitive spectrographs, its orbital parameters would remain crude. Each advance in instrumentation has peeled back another layer of complexity, revealing the system not as a simple binary, but as a dynamic interplay of matter and gravity. This binary therefore represents both a scientific object and a historical trajectory. It was the first stellar mass black hole to be widely accepted, and it has remained at the center of observational astrophysics as instruments have improved. From the first counts of X-ray photons in the early 70s to detailed spectra timing polarization and images today, the system has traced the evolution of high-energy astrophysics itself. It remains a target for every new mission, not only because it is important, but also because it is bright, persistent, and nearby enough to serve as a natural standard. Even though decades of observations have established the presence of a black hole in this binary system beyond doubt, several aspects remain uncertain and continue to be studied. One of the most important questions concerns the exact spin of the black hole. Spin affects the location of the innermost stable orbit, the efficiency of accretion, and the ability of the system to launch jets. Two main methods are used to estimate spin. One is modeling the thermal spectrum of the accretion disk fitting the temperature distribution to determine how close the disk extends to the event horizon. The other is modeling the broad iron K-alpha line fitting its shape to measure relativistic effects. Both methods suggest that the black hole is spinning rapidly close to the maximum allowed by general relativity. However, the exact value depends on assumptions about the disk's inclination, atmosphere, and structure, so uncertainties remain. Another unresolved issue concerns the geometry of the corona. Observations show that the corona produces the hard X-rays through inverse Compton scattering, but its size and shape are debated. Some models place it as a compact sphere near the event horizon. Others describe it as an extended layer covering the disk. Recent polarization data suggest that the corona may be elongated along the disk axis, perhaps forming the base of the jet. Distinguishing between these models requires more precise measurements of timing, spectra, and polarization. The corona is central to the system's variability, so understanding its geometry is crucial for interpreting the X-ray emission. The structure of the stellar wind of Henry Draper, catalogue number 226,196, is another area of uncertainty. The wind is clumpy and variable, producing fluctuations in the accretion rate and dips in the X-ray light curve. Ultraviolet spectra show complex absorption features that change with orbital phase. Modeling these requires accounting for ionization by the X-ray's radiative transfer and the hydrodynamics of clumps. The uncertainties in the wind affect the estimates of how much mass is being accreted, the feeding of the disk, and the long-term evolution of the binary. Astronomers continue to improve models of stellar winds in massive binaries, but challenges remain. The connection between spectral states and jet activity is another open problem. The radio emission associated with jets is strongest in the low hard state when the corona dominates, and weakest in the high soft state when the disk dominates. This correlation suggests that the geometry of the accretion flow determines whether a jet is launched. But the physical mechanism linking coronal strength to jet production is not fully understood. Theories invoke magnetic fields threading the disk or the black hole's spin, but the balance between these contributions remains uncertain. Determining this balance is important because it may apply universally to black holes of all masses, from stellar binaries to supermassive black holes in galaxies. The evolutionary history of the system also presents questions. The relatively low velocity of the binary through the galaxy suggests that the black hole did not receive a strong kick when it formed. This points to direct collapse as the formation mechanism, rather than a supernova explosion. If so, then very massive stars can collapse quietly into black holes without disrupting their binaries. This has implications for the population of black holes in the galaxy and for the progenitors of gravitational wave sources. However, uncertainties remain in the modelling of massive star evolution mass loss and the details of collapse. More data from similar systems are needed to confirm whether direct collapse is common. The inclination of the orbit is another parameter with small but important uncertainty. Estimates range from about 27 to 35 degrees. Even this small range affects the derived masses and spin estimates. Constraints from ellipsoidal variations, polarization, and interferometry help narrow the value, but refinements are still needed. Future instruments may provide tighter limits, reducing the uncertainty in all other properties derived from inclination. The long-term fate of the binary is also uncertain. The blue supergiant will eventually exhaust its fuel and collapse. Whether it forms a neutron star or another black hole depends on its mass loss and core structure. If it forms a black hole and the system remains bound, the result will be a binary black hole. Over billions of years, gravitational radiation will cause the orbit to shrink, leading to a merger and a burst of gravitational waves. Whether this happens depends on details not yet known. The system thus represents not only a present-day X-ray source, but also a potential future gravitational wave source. Accretion itself presents mysteries. Simulations show that gas should settle into a relatively smooth disk, but observations reveal turbulence, flickering, and quasi-periodic oscillations. These reflect magnetohydrodynamic processes that are not yet fully understood. Magnetic fields may drive turbulence and angular momentum transport through the magnetorotational instability. Reconnection events may produce flares. Pressure instabilities may create oscillations. Matching all these processes to the observed timing signatures is an ongoing challenge. The system provides real data to test theories of plasma physics in extreme conditions. Some uncertainties stem from observational limitations. Even with modern satellites, data have finite sensitivity, resolution, and coverage. Background noise, limited photon counts, and instrumental effects introduce errors. Observations at some wavelengths, such as extreme ultraviolet, are difficult because of interstellar absorption. Coordinated multi-wavelength campaigns are needed to capture the system's behavior in full, but such campaigns are challenging to organize. As technology improves, many of these limitations will diminish, but some will remain intrinsic to the difficulty of studying objects thousands of light-years away. Despite these uncertainties, the fundamental conclusion that the compact companion is a black hole remains secure. The uncertainties instead define the frontier of knowledge. They show where theory must be improved, where new instruments are needed, and where future discoveries may lie. Cygnus X-1 has moved from being a candidate to being a benchmark. It is not only the first widely accepted black hole, but also a continuing subject of inquiry, revealing new puzzles even as old ones are resolved. Each open question provides motivation for further observation analysis and theoretical development, ensuring that the system remains central to astrophysics. The binary system in Cygnus has been observed for more than 50 years, and its persistence as a bright X-ray source has made it a cornerstone of high-energy astrophysics. Unlike many X-ray binaries that flare dramatically and then fade into long periods of quiescence, this system remains active and luminous, with variability that never ceases but with emission that is reliably detectable. Its stability has allowed astronomers to return to it repeatedly, with each new generation of instruments turning it into a long-term laboratory for studying accretion compact objects and strong gravity. Continuous monitoring programs have established that the system spends most of its time in the low hard state, where the spectrum is dominated by hard X-rays from the corona and where the jet is present. In this state, the light curve shows strong rapid variability, quasi-periodic oscillations and broadband noise. Occasionally the system switches to the high soft state where the thermal emission from the accretion disk dominates and the corona weakens. These transitions are accompanied by changes in timing properties and by reductions in radio emission. The alternation between these two states reveals how accretion reorganizes itself, sometimes favoring a hot dynamic corona and sometimes favoring a cooler stable disk. Space-based observatories such as the Monitor of All-Sky X-ray image aboard the International Space Station, the Neil Gehrels Swift Observatory, and the Fermi Gamma Ray Space Telescope have provided continuous light curves over decades. Their data reveal both short-term flares and long-term trends. They have captured the irregular timing of state changes, showing that transitions do not occur on a fixed schedule, but are triggered by changes in the stellar wind feeding the black hole. This variability underscores the complex feedback between the supergiant's wind and the accretion flow. Ground-based telescopes add complementary data. Optical spectroscopy continues to refine the orbital parameters of Henry Draper Catalogue number 226,196, while photometry tracks its brightness variations caused by tidal distortion. Polarimetry measures how scattered light changes with orbital phase, constraining the geometry of the disk and corona. Radio arrays such as the Very Large Array and the Very Long Baseline Array monitor the jet, detecting changes in flux and mapping elongated structures. These radio observations confirm that the jet strengthens during the low hard state and weakens during the high soft state. Together, these data across multiple bands show the system as a dynamic interplay of components. The long baseline of observation has revealed secular changes in addition to short-term variability. Measurements of the orbital period have shown small but steady decreases, indicating that angular momentum is being lost from the system. This loss may be caused by mass loss through the stellar wind, or by the emission of gravitational radiation. Although the effect is subtle, it accumulates over time, showing that the binary is evolving. The gradual tightening of the orbit has implications for the eventual fate of the system when the blue supergiant exhausts its fuel and collapses. The persistence of this binary has also allowed astronomers to test and refine models of accretion physics. Simulations of magnetohydrodynamics in curved spacetime predict patterns of variability and state transitions. By comparing these predictions with long-term light curves and spectra, researchers assess the accuracy of their models. When simulations reproduce observed features, confidence grows. When they fail, new physics must be added. The binary in Cygnus thus serves as a benchmark not only for observation, but also for theory, continually challenging models to match reality. The system has also influenced the broader context of astrophysics by connecting X-ray astronomy with gravitational wave astronomy. The discovery that the compact companion has a mass of about 20 solar masses demonstrated that heavy stellar black holes exist in binaries. This finding paved the way for interpreting gravitational wave detections from merging black holes with similar masses. The binary in Cygnus is not expected to merge within the lifetime of humanity, but its existence showed that such systems can form and survive. It provided the first observational anchor for the idea that massive binary black holes are real and detectable. Future instruments promise to deepen knowledge further. The Athena X-ray Observatory, planned by the European Space Agency, will bring higher spectral resolution and sensitivity, allowing the iron K-alpha line to be studied with unprecedented precision. Polarization will be measured with greater accuracy, clarifying the geometry of the corona. Radio arrays, such as the Square Kilometre Array, will map jets and outflows in finer detail. Infrared interferometers will refine measurements of the star's shape and orbit. Each advance will reduce uncertainties in mass spin inclination and accretion geometry, sharpening the portrait of the system. The significance of this binary lies not only in its role as the first confirmed stellar mass black hole, but also in its continuing contributions. It remains bright enough to be observed easily, stable enough to be tracked over decades, and complex enough to challenge understanding. Its lessons extend beyond a single system to black holes in general, informing theories of how matter behaves under extreme gravity, how jets are launched, how winds interact with radiation, and how binaries evolve. Every new dataset adds detail to the picture and provides fresh tests of physics. As time passes, the blue supergiant will continue to evolve. Within a few million years, it will exhaust its nuclear fuel and collapse. Whether it forms another black hole and whether the binary remains bound are questions that will determine the system's ultimate fate. For now, it remains a luminous beacon in the galaxy, a constant source of high-energy radiation, and a reminder of how far astronomy has advanced since the first crude X-ray detectors pointed to the sky. It is both a historic discovery and a living laboratory shaping the understanding of compact objects from its discovery in the 1970s to the present day.